Okay, we're going to work through some practice problems for the 2020 practice problem handout for this coming midterm 3. So let's start with question 1. Which of the following are conditionally convergent? And we have these following 3 series. Series number 1 is this one. Classic alternating series. Series number 2 is this one. And series number 3 is this one. Oops. Okay. So let's remind ourselves what it means to be conditionally convergent. So if this blob denotes the set of all convergent series, okay, we know that the set which are absolutely convergent are a strict subset. Okay, so this red blob are those which are absolutely convergent. Because if you're absolutely convergent, you are indeed convergent. Okay? And there are some that are convergent, but they are not inside this red blob. They are not absolutely convergent. And if you're one of those are the guys we call conditionally convergent. Okay? All right, so if we are not absolutely convergent, what does it mean? It means that when we take the absolute value signs around the terms of the series, then that thing will not converge. So let's look at the first one. So firstly, we know it definitely does converge. It's just an alternating series, right? These terms 1 over n are decreasing, and the limit as it goes to infinity is 0. So it's definitely converging. So by alt series theorem test. But if we take this goes into infinity, 1 over n, which is the absolute value of these terms, diverges. So sure enough, this thing does not converge absolutely. So if this guy lives in here, it lives in here, in this region. Cool. Let's do another example. Change colors. Let's do not another example, but the next example, 2. All right, so again, this guy is definitely going to converge just by the fact it's alternating and the terms are decreasing, right? And the limit is 0. But if we take the absolute value of these terms, so we get this. And sure enough, that will converge. It is going to 0 fast enough. 3 is bigger than p. So recall the p test. If we have the sum of 1 over n to the p, if p is bigger than 1, then it will converge. And that follows just from the integral test. Okay? Converges. So not only does this thing converge, it converges absolutely. So this guy lives right here, right? So actually, let's put in these guys. So this is where I is, and I is right here. Okay, change colors again. Let's keep with the orange. Let's look at 3. Again, this guy's an alternating series. The terms are going down to 0. They're decreasing. So it's definitely going to converge. But if we take the absolute value of this, then this diverges. By p-test. Maybe point out, so I should say by p-test here as well. Okay. P is less than equal to 1, and here P is bigger than 1. Okay, cool. So this guy does indeed converge in this form, but when we take the absolute value of the terms, it diverges, so it's conditionally convergent. So I also lives here. So red color, so I lives here too. So that's our answer. So we have that I and I are conditionally convergent. And that's it. Those are the only two. And that is option C. Okay. Let's do another one. Let's put that in here. Which of the following series converge? So I'll write them down. This is question 2. So we have the first series. The second series. Third series. And fourth series. Okay, so the first series should be a dead giveaway that we're going to use the root test because it is a series whose terms are taken to the end. So solution I Okay, and when we're at this point, then we're in a very familiar limit problem, right? So as n gets bigger and bigger, this 1 and this 6 here are less and less important. So just dividing through by n, for example, we find that this limit is just 1 over 2. Okay, so morally, when we take, we should take the absolute value signs, strictly speaking, but we don't care because everything's positive. When we take this guy to the nth root, we get 1 over 2, which is kind of like saying that an is an awful lot like 1 over 2 to the n. In other words, in its bones, this guy, despite the exterior complications, this guy is morally like just the geometric series 1 over 2 to the n, right? So, definitely will converge. So the theorem is that since this is less than 1, it will converge. So converges. And converges absolutely. So it doesn't ask us, it just says which converges, but we know for free when we do the root test, then this thing actually converges absolutely. We have something which is going to 0 so fast with the root test or the ratio test, it will converge absolutely. Cool. So that is question 2 part, well, that's series 1 of question 2. Let us do the other series. Consider the second series, which is this thing. Okay, so the only thing we have to remember is that E is just some specific number. So recall E is 2.71 and blah, 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 some other digits. So E over 2 in particular is just bigger than 1, right? So this series converges by the p-test. Okay, so maybe they're trying to trick you a little bit putting E here. Maybe you think something strange is going on, but it's just remembering that E is just a specific number. The exponential function E to the x is just some number to the x, and the only reason E is chosen is because when we differentiate that guy, we get E to the x again, right? So nothing difficult, nothing too deep going on here. Let's do this one. This is 3. Okay, this guy is a little bit harder. So you remember when we were talking about series and the section on strategy of series, I told you that this is a little bit analogous to integrals. So when we finished learning all these integration techniques, then we would just have an integral placed in front of us, and you'd have to think about your toolbox of techniques: integration by parts, U sub, trigonomic substitution, all these different things, and use them, maybe use them in combination to figure out an integral. And it's just a matter of practice and instinct that you will learn which tool to use for a certain integral. Well, series are a little bit analogous. So we went through a list of strategies with a bunch of methods to try and determine if a series converges. And the very last guy on the list was the integral test. And it was the last guy on the list because it's one which actually requires us to do a calculation rather than just do a limit. However, it is a very natural and very powerful test. So let me try and show you how you're going to get here. So this guy right here, none of the obvious things will work, right? It's not it's not 1 over n to the p. It's nothing we can apply to the p-test. If you are used to this kind of, well, if you look at this, you should be able to see this is not going down to 0, anything like a geometric series or faster than a geometric series. This guy, if it's going down to 0 fast enough to converge at all, it's a very narrowly run thing because it's only a little bit smaller than 1 over n, right? 1 over n we know it doesn't converge. So there's no underlying structure analogous or even faster decreasing than a geometric series. So the ratio and root test, they're not relevant. What else? What could we compare it to? The only thing I can think to compare it to is 1 over n. But 1 over n diverges, so showing something which is, since this is less than 1 over n, having something less than something diverges really says nothing, right? So that's no good. Limit comparison test, what could we possibly marry this guy to? Not really anything, right? There's no obvious guy to marry this guy to. I mean, the only thing it looks close to is 1 over n, but 1 over n, the limit ratio of this guy with 1 over n isn't going to be some finite positive number, so there's no limit comparison test. There's none of the easy tests work. So by a kind of process of exclusion, you should sort of go, okay, the issue with this guy is how fast these positive terms go down to 0. I don't have any other tools I'm going to have to use the integral test. So let's do a little recap of the integral test. So recall, if we have a series of positive terms, okay, oops, we can represent them in a picture like this. I want to put it here, let's put it here. So from 0 to 1, let's put a block like this, whose height is A1. And then from 1 to 2, let's put a block like this, whose height is A2. And then this guy would be, say, A3. And then so on. 3 to 4, we have A4, and so on. 4 to 5, so on and so on and so on. Let's put this guy actually in here, just to have a nice picture. Say 4. And the integral test if we have a function f which is decreasing and f of n equals an, then this series converges if and only if integral from m to infinity f of x dx converges for any m. So do not get hung up about which m you're going to put here. It's for any m. Because the issue of whether or not this series of positive term converges is the issue of when we start summing from any particular position, because the sum of 1 up to any number is just a collection of finite numbers. Of course, that makes sense. That converges. So if we sum from 1 up to 100 trillion billion, all good. We don't care how big it is. It's meaningful. It's a meaningful thing. But summing from 100 billion trillion onto infinity, that is a thing that might diverge, right? So the first finite number of terms we just don't care about in terms of whether or not it just doesn't affect the convergence, right? So for that reason, we can have any number here. So don't think about trying to match this, something from n equals 1 or 2 or anything to this. We don't care. We don't care at all. Just put anything in here. If this thing converges, you're all good. If it doesn't, you're not good. Okay? And incidentally, whether or not this converges, if it converges for some m, then it converges for any other m for the same reasons, actually. Okay, let's see why this is true. And as always, it's a picture. So let's represent the function f. Okay, so f is defined by this. So f at 1 is a1, right? So it's got the value right here. F of 1 is a1. F of 2 is a2, so it's here. F of 3 is a3, so it's here. F of 4 is a4, so it's here. So we have a decreasing function like this. A decreasing function like this. So this is our function f. And all these blocks lie underneath the graph of this guy, right? So if we know, so if the integral from m to infinity of f of x converges, yeah, then that means that the area underneath this graph is finite, so the area of all these blocks, and we add them all together, is also finite, so therefore we are all good. So that means that then since the sum from k equals m plus 1 to infinity, a k is less than this thing, just from the picture, right? The series converges. Cool. All right. That's one way, and that's somewhat the easier way. But there's also the opposite implication. So if this thing doesn't converge, if the function, when we take the integral from m to infinity, doesn't converge, then this sum also diverges. And we can't tell that from this particular picture because f lies on top. But we make a rather small change, right? So this is what we do. So let g of x just be f of x plus 1, right? If we have g defined in this way, let's change color to red, then g of 1 is f of 2, which is a2. So g of 1 is here, right? G of 2 is f of 3, which is a3, which is here. G of 3 is f4, which is a4, which is here. So this function right here, g lives underneath. G lives underneath, okay? So this is our function g. Okay, so consistent. So if the integral from m to infinity f of x dx diverges, what's that? If we do a sub and we let x be this, then this is the same as the integral from m minus 1 to infinity g of x dx diverges. Oops. Which is saying that the area underneath the red graph here is infinite. Right? So this is called infinite area. And it lives underneath these blocks, right? Which means that the sum of the areas of the blocks is infinite. So this series to infinity, an diverges. Just pictures, right? Cool. So in our particular guy here, running out of space, so we just take f of x be this guy, x over the square root log of x, right? And we have to consider this integral. We can start from any number. Let's start from 2. And this should seem like a fairly familiar integration problem we'll solve with a u sub. So if we let u be log of x, typical strategy is you put u inside the, if you have a square root of something, try and make that the sub. And then we do du by dx is 1 over x. We do the u sub, and then we're going to do the integral from 2, oops, not 2, from log 2 to infinity of 1 over square root of u du, right? And this thing diverges because, again, by the p test for indefinite integrals, here we have p equals a half, so it diverges. Yeah? So the answer is that series 3 diverges. Okay, so I did a little recap of the integral test, but the actual solution of the problem is pretty quick once you identify that you have to use the integral test. So just think about what you have facing you here. It's a sequence of positive terms. The issue is it going to zero fast enough? None of the standard tests will tell you that. This guy, the integral test, is kind of like the definitive test, right? So this thing is equivalent to the integral of the function f from any number to infinity. And the good news about this is that we have this powerful tool of calculus, right? We have the fundamental theorem of calculus. We know how to integrate things. We know how to find antiderivatives, and we are all set. So interestingly, if we try to solve this problem before the invention of the fundamental theorem of calculus, then we'd really have to really struggle, right? We just wouldn't be able to do it. But with this very powerful tool that we have, we can answer this question. Cool. Let's keep going. So our final series for this question is this guy. Okay. So it's a sequence of positive terms. The issue is, does it go to 0 fast enough? And hopefully you can see pretty quickly that it does. In fact, it's going to 0 incredibly fast. So by comparison test, we know that 1 over n to the n for sure is smaller than 1 over n squared for n bigger than or equal to 2. So converges. And that's it. Cool. So what did we learn? We learned that series 1 converged by the root test. Series 2 just by the p-test. Series 3 doesn't converge. Series 4 converged just by comparison test. So we have 1, 2, and 3 converge, which is option E. Okay. Let's do another one. Which of the following converge? First series. N equals 1 to infinity minus 1 to the n over e to the n. Actually, let me just do them one by one rather than write them all out. So this is our first guy. So let's think about whether or not this converges. What do we notice right away? Firstly, it's an alternating series. It probably is the case that it's going to converge just by the alternating series test because the guy on the bottom is decreasing, or the guy in the bottom, e to the n, is increasing a lot faster than n is increasing, so the ratio of n over e to the n should be decreasing. But if we think a bit more about the rates at which these guys are doing their thing, so n is certainly growing, but e to the n is growing so much faster, right? E to the n, it's the exponential function, just applied to the integers. It is killing n, which is just a linear function, y equals x. So it shouldn't be an issue that this thing is converging. It should even converge absolutely, forgetting about the fact it's alternating. All right, so thinking a little bit more, what does it look like? What is the essence of this thing? What is it like at its bones? Some experience should tell you now that when something is going to 0 really, really fast, and then we just multiply it by n, if it's going to 0 like a geometric series, then the n is not going to dramatically affect it. It's just going to be in a sort of an irrelevance to this thing is like a full-on steam train going down to 0, and the fact that we multiply it by n shouldn't make a difference. And we can detect that with the ratio test. So that's right on our thinking. So looks like a series going to 0 or a geometric series in its bones. So ratio test. So let's take an to be these guys, minus 1 to the n over n e to the n. And then if we take an plus 1 over an, what do we see? The minus 1's just disappear. We're going to have n over n plus 1, and then we're just going to have 1 over e, right? So we take the limit as n goes to infinity, an plus 1 over an. This is the same as 1 over e, the limit as n goes to infinity, n plus 1 over n, which is 1 over e, right? So, converges since, by the ratio test, converges since 1 over e is definitely less than 1, and in its bones, this guy, or the absolute value of this guy, is kind of like just 1 over e to the n. Okay? Because each term is just, to get from the nth term to the nth plus 1 term, you're just basically multiplying by 1 over e, right? That's what this thing says. So this is basically like this geometric series, and it converges. Cool. So that's the first guy. Let's change colors. Let's do the second guy. Which is this thing. Okay, so it's a sequence of positive terms. The issue is it going to 0 fast enough? And hopefully you can quickly identify that it is, because this guy is actually even more quickly going to 0 than a geometric series. It is m factorial, so converges because you can compare it to almost anything. It's going to go 0 faster, right? So because m factorial is m times m minus 1, blah, 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 like this. So in particular, it is bigger than m squared over 2 for any m, right? Just because of the first two terms. Oops. Any. Okay, so by comparison test, since 1 over m factorial is definitely less than 2 over m squared, and the sum m equals 1 to infinity, 2 over m squared converges by the pretest, series converges. Okay, cool. Next guy. Running out of space. Let's see if we can squeeze in this guy, I333. This guy is sum from n equals 0 to infinity minus 1 to the n factorial 5 to the n. Okay. All right. So if you look at this guy, let's just try and identify what was happening. So it's alternating. So all we need is that these terms just go down to 0 and are decreasing. But what are they actually doing? So we have n factorial over 5 to the n. So notice n factorial is n minus 1, n minus 2, blah, 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 all the way down to 1. And there are n terms. Okay. So when we consider this ratio of n factorial over 5 to the n, then we have like 5 times 5 times 5 and so on, right? So there are n terms on the top and there's n terms on the bottom, but the guys on the top are going to be way bigger as n goes towards infinity, right? So we have 1, 2, 3, 4, 5. Those guys are smaller than 5, 5, 5, 5, right? But then all these guys are bigger and there's more and more of them. So actually this thing is going to infinity. And as we know, the only way a series converges is if the step size goes down to 0. So by the divergence tests, which is exactly what I just said, that the step size has to go to 0, since this guy is actually not going to 0, it's even going to infinity, can't possibly converge, so it does not converge. Okay. So as you notice, a lot of these questions you can just answer very quickly if you've built some kind of intuition about how to do this. And that just comes from doing this often enough, doing enough practice with this. Okay, let's do some more of these. So we have our final series, which is IV, which is this guy. So it's alternating, okay, but let's see how else we can write this. So this is also can be written like this, 0 to infinity. Let's pull out this as -1 to the n, and then it's like 2 to the 3 to the n. Okay, so it's alternating, but even if we take the absolute value of all these terms, then we just see it's a geometric series. So it actually converges absolutely. So since this guy n equals 0 to infinity is a geometric series, we even know it converges. We even know what it converges to. It's not needed though. The series converges absolutely. And so converges. Okay, so that's all of this stuff. What did we learn? So we learned that the first series converged just by the ratio test. So I converged, I converged, I did not converge, and this one converges. So we have 1, 2, and 4 converge, which is option A. Okay, let's do question 4. So this time we have these two series, S1, which is this thing, n equals 1 to infinity, -1 to the n, 3 to the n, over n, 2 to the n, and S2, infinity, sine of n over n squared. Okay, and so we have a bunch of multiple choice options, which are basically various options of the kinds S converges conditionally, or diverges, or converges absolutely. So if we know exactly whether or not this thing converges and how it converges conditionally, absolutely, or whatever, and the same for S2, then we'll know what multiple choice option to get. So let's just figure out as much as we can about the convergence otherwise of these two series. So let's look at S1. So it's alternating, first thing to notice, but if we look at, just ignore the fact it's alternating, just take the absolute values of this thing, then notice, oops, that this thing can be written like this. Okay. When we take the absolute values of S1. So what about this guy? Well, it looks somewhat like a geometric series with 3 over 2, but we have this 1 over n, and you might think, okay, maybe it's still gonna converge, but hopefully you know by now that when we have something geometric fighting against something polynomial, in this case just linear, just n, then the geometric thing will definitely work. But if we're in any doubt, then what we do, it looks a bit like a looks a bit like a geometric series, so we're going to use the ratio test, which is exactly a tool to detect if a series in its bones is a geometric series. So apply ratio test, and then we're going to let an be these terms. Okay. I should maybe write a sentence. Notice this looks geometric. So then what happens when we take the limit as n goes to infinity of an plus 1 over an, then we are going to have n over n plus 1, the minus 1's vanish, and we are going to have just 3 over 2. Right? I should put the limit signs. We just put it in here. Okay. And then the 3 over 2 we can just pull out. So then this is the limit as n goes to infinity of n over n plus 1, which is just 3 over 2. And that's it. So this is bigger than 1, so it diverges. And what this confirms is that at its heart, this thing is like the geometric series 3 over 2 to the n. So this thing diverges, and that's it. We don't have to think anything more about that. Cool. All right, let's look at S2. Change color. So if we look at S2, it's not any more sequence of positive terms, but it's also not alternating because sine n is not going to go plus minus, plus minus, plus minus, right? We know what the sine graph looks like. And if we just consider the integers, then it's not going to nicely alternate signs necessarily. So this is not something where we can just apply the alternating series test. However, if we simplify matters and take the absolute value, what do we notice? Well, then it does become a sequence of positive terms, and then how fast does it go to 0? So look at the sum n equals 1 to infinity, absolute value sine of n over n squared, okay? And then the issue is just how fast does it go to 0? Well, sine of n is always going to be some number between minus 1 and 1, so the absolute value is going to be some number between 0 and 1. So this thing in particular is going to be less than this. Yeah? Should actually be a bit more formal than that. Well, I said, just wrote is true, but let's put it in the format we've been teaching you. So notice that sine of n over n squared is less than 1 over n squared, and the sum from n equals 1 to infinity 1 over n squared converges. So let's call this thing star. So star converges by comparison test. And therefore, our series S2 converges absolutely. Okay, cool. So, hopefully, these questions seem fairly routine. And as always, if they're not, then this is an opportunity for you to identify your weaknesses, try to see what misunderstandings you have, try and close those gaps. All right, so that's it for today.